What did you get, Charlie Brown?
I got a rock. I got a rock. Rock. I got a rock. 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 I got a rock. I got a rock. I got a rock. Rock. Rock.
What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock.
What did you What did you get, Charlie Brown?
I got a rock. I got a rock. 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 I got a rock. I got a rock. Got a rock. Got a rock. 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 I got a rock. I got a rock. 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 I got a rock. I got a rock.
All right, so we'll go ahead and start. We'll probably end a little bit earlier today because I got to skedaddle. But what I hope to do by the end of the day is just to finish up with the disjoint set coverage that we were talking about, and then to look at an alternative algorithm for minimum spanning trees. So when we last left it off, we left it off with this visualization, right? Where you have a bunch of disjoint sets and you want to eventually union them all together. And the way that you do that is by representing them as trees. And two nodes are in the same tree, then that means that they're in the same set. Now, what you do when you combine the sets, there are several operations, of course, that you can support. One of those is to initialize. And initialization is really easy because all you're doing is creating a bunch of single node trees, right? Now, there is a gotcha here, and I'll show you that in my implementation, that we also want to maintain a reference to each one of every single node so that if you ask me for the node representing 5, I can immediately give you that node and so that I can traverse back up to the parent node or the root node in that tree to find its representative, all right? So the way that I did that in Python is I defined a disjoint node, a disjoint set node, I should say, Note here that, does anybody know what the convention here is with an underscore? Generally, that's private, right? There is no private keyword. There is no strong encapsulation in Python. So we keep this as an underscore as a convention to tell you, don't mess with this, right? It's kind of like the magic functions here with underscore underscore. Don't mess with this, or it's built in. It's something special. It's something different. Every node will keep track of the item, its ID, which is just associated with integers 0 through n-1 when you initialize the tree. There's a rank here that we'll talk about in a second. And then, of course, we're only keeping track of the parent, not all of the children. Remember, it's not a binary tree. You could have 5, 10, 15, a million children, right? We're only keeping track of the parent so that we can go up, 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 up to find our representative, right? We have this convenience function here that says, if my parent is none, I must be a root, right? And then we've got a nice string method here that prints it out, prints out the item, its ID, its rank, and then what its parent is so that you can go and check who's the parent. Right? Now, there are a couple of operations here. For example, find in a set. If I gave you an item, I should be able to find the representative of that set. And all we're doing is calling this internal function right here that sets a current node and traverses up the ladder, up the tree, until it finds the root node. But now also we're collapsing it if appropriate. Remember that operation that I showed you last time? That as you go up, everything along the way will be collapsed so that that tree remains as shallow as possible. And so that's what this is doing here. It traverses not only once to find its representative, but then it'll start the process all over again, making sure that these are all collapsed all the way up. Is same set is simply just finding whether or not you have the same representative. That A and B are in the same set if you go up and you find that they have the same root node. Right? Then the other operation is a union. Now the union is simply just if there are, well, first of all, if they're in the same tree, you don't do anything. Right? False. Right? Otherwise, what you do is you've got now two trees. All you're going to do is take this tree and append it to the root of that other tree. But you want to do it in such a way that everything remains efficient. So what's going to happen is, I believe that it's, you always append the smallest to the largest. Or maybe it's the other way around, I forget. But anyway, that ensures that you're going to keep, that's what makes the analysis nice and clean. Yeah? Well, you've got these two big trees, right? So, for example, let's just go ahead and look at something with only two trees of rank 2. There we go. All right. This one, so that's where this rank comes in. The rank here is 2 because it is of a depth 2 initially. This has a rank 2, so it's of depth 2. But now there's no smaller one here. So when we actually union these two together, say 1 and 8. Right? Let's watch that operation. Right? So you have to find the representative first of both of these. And by the way, as you found the representative, 8 is going to end up going to up to make sure that you have everything shallow. Good. And 0 becomes the a new child of the other one. And it increases its rank. Why? Because if you have a rank 2 tree that you just appended to a new node here, you have a potential for 1, 2, 3. Now, it's not going to be the 1, 2, 3. It is the case in this case, that it's now a depth 3 tree. And by appending these, let's see, do I have, can I, all right, I'm not going to be able to add a new one here to show you if it's smaller to larger or larger to smaller, I forget. It's really just a small detail anyway. Right? Okay. So let's see this in action here. What I did is I took the example from last time and I simplified it so that we have A, B, C, D, E, F, G. That is going to be 7 things. So let's simulate it over here with 7 things. Right? And what I do is I union, first of all, I print it out. And I showed you that we can find a representative. Initially, everything is its own representative. But as we start unioning things together here, A to B and then B to C, what does that look like? Visually here, I will union, and here that's just going to be 0 through 6. So I will union A to B. And you've got now a 2-node tree. I will union B to C, so 1 to 2, go. And note here that it was able to find 1 as the root, and that's the representative of that set, right? Again, I'm going to draw your attention to the fact that I also had to use a ItemMap here, that the representative 0 through n-1 is going to be associated with an actual node here. Right? Every time I create a node in my initialization, I make sure that that's in the map so that I can look it up for free, basically. Right? And this is a hash map, or well, it's a dictionary in Python, but it's a hash-based data structure. So it's essentially amortized constant time. Right? Then I print it out. Let's make sure that it's actually working still here. So Python 3 disjoint set. Oops, sorry. There we go. So I've got the entire thing here. But after I've unioned A and B, or A, B, and C together, then we have this this printout here. That B, its parent is A, C, its parent is A, and then the parent of A is none. It's already a root. Right? So let's do the same thing for 3, 4, and 5. Let's collapse those. 3 goes to 4. Let's say 4 goes to 5. And that ends up creating 2, I'm collapsing these down until I have only one set. And now, so I've done the same thing for E and F here. And now let's go ahead and do the last thing that I did, where I combine both of those trees, or B and E here. In other words, something in this tree, say 1 for B, and then what's E? A, B, C, D, E, 5. There we go. And you'll see that since these trees have the same rank, the same depth basically, that appending one to the other, it doesn't really matter which way you go, at least in this case, because they have equal rank, but you end up with this tree. Right? So over here, what I did is I ended up with this tree. B and C, their parent is A. That's like these two right here. And then E and F, its parent is D, and then D's parent is A. So it looks like these two, 0, 1, 0, 2, 1, and up to 4. Right? Yeah?
Does it matter which node you say union these two nodes together?
Well, that's where you look at the rank. You always put the smaller rank as the child, the higher rank as the parent. But if all things being equal, and let's take a look at the code that I wrote for it, all things being equal, it looks like I go one way or the other, right? Here, I could change this to less than or equal to, and then it would prefer doing it this way. Otherwise, this is the preference for equal rank trees, right?
So there's any benefit in joining the lower rank?
Yes, in fact, you have to. Otherwise, you won't get the performance. You don't. But the efficiency analysis on this is beyond the scope of this course. But I can give you a handout that tells you why that's necessary. But that's, I mean, it's not that complicated of an analysis. But I really don't like the analysis anyway, because at least for the use case that we have, we always start out with a bunch of single node trees. As long as we're doing this maintenance of, okay, well, now I need to find the representative of 2. What's going to happen here? Find set of 2. That's going to end up being collapsed, right? So throughout this entire process, when I'm looking stuff up, I'm also collapsing at the same time. you'll never get above, I mean, you can even do a tighter analysis, I believe, that shows that you'll never really get above like almost a constant depth. And if it's a constant depth, then all these operations become essentially constant, amortized over the lifetime of the data structure. And in fact, that's the beauty of the data structure. Yeah, here, let me go ahead and cut and paste the rest of this for you, and then we can talk about it. All right. So, find set. All right. So find set returns a representative of the set containing U, and all that is a hash map. You automatically grab the node, and then you traverse up to its parent, up to its root. And so that's going to be proportional to the depth. Same set, all you need to do is do 2 of those operations and return yes or no that they have the same root. Union of U and V, it combines the set containing U and the set containing V into one new set. One of the essential details here is that when you're unioning, I don't know if that's a word or not, spell checker doesn't like it, but unioning 2 sets together, we always attach the smaller to the larger according to the rank. And that ensures that the depth will be at most logarithmic, and even that is not a very tight analysis. Yeah?
So if we're trying to attach, like if we give it like a UV where U is deeper than V instead of shallower, we could just switch U and V around.
Yeah. You look at the rank according to the that's being stored as part of the node itself. That's why I put it in the node, so that you could, and then the rank doesn't ever change. The rank isn't that's why it's called rank and not depth. It's an overestimate on the depth of the tree. The depth will never be larger than the rank. And so if you take the larger tree, it could be equal size, and attach the smaller tree to the end of it, then you will not increase your rank. Unless, actually you will increase your rank because you'll take this +1 or something like that, because you might have increased the depth, but in all likelihood you didn't. But again, the rank is not the depth, the rank is an estimate on the depth. It's an overestimate on the depth.
But we would still need to update it.
Potentially, yeah. In fact, how do I do it? Rank is equal to the rank of both trees, plus.
There we go.
Right. The efficiency depends on the height of the trees, the depth of the trees, of course, which you can show through that analysis that I'm omitting is at most logarithmic. And therefore, all these operations are logarithmic. But overall, you can get an even tighter analysis and show that over the lifetime of the algorithm, when you take the sum total of all of your operations, it's only going to be order n, right? Because you're taking the number of trees and you're decreasing the number of trees every single time, but you're also making sure that they all stay shallow, shallow, shallow. And so some operations will be more expensive than others, but in the long run, when you take, this operation will be more expensive, this operation will be cheaper, this is more expensive, but cheaper, cheaper, cheaper. When you take the average of them all over the number of operations that you're actually going to execute, n, because you start out with n nodes, then on average, each operation is only constant time. And since you do n of them, well, then it's only order n, which completely is eclipsed by Kruskal's original algorithm, which was, remember, you had to sort the edges first, m log m. So your sorting becomes the most complex part as far as efficiency goes. Right?
So Kruskal's is still better.
Well, I mean, better than what we have only looked at one.
Oh.
We've only looked at one minimum spanning tree so far, and it's order m log n, or m log m, which is the sorting the edges. Now there is an alternative called Prim's algorithm, right, that we'll talk about today here, and it approaches it in a completely different manner. What it does is it works by starting at a vertex and building a connected tree outward. So with Kruskal's algorithm, because you are always considering, you could consider an edge over here, and then you could consider an edge on the other side of the graph somewhere completely different, because that's the next least weighted edge. What we're doing is we're starting locally, and then we're building outwards. Right? It's kind of like BFS in that way, but your criteria for going to the next vertex is completely different. Vertices are separated into 3 sets. Right? One of them are the tree edges, or tree vertices, excuse me. Vertices that have been added to the intermediate MST, minimum spanning tree. Right? You have fringe vertices. Vertices connected that have been seen, i.e. are connected to tree edges, and you have, or tree edges, tree vertices, there we go, tree fringe, and what's the other one, unseen vertices, right? Vertices that are not connected to the tree yet, right? Or that are not part of the tree nor connected to the tree yet, right? So what we're going to do is we're going to consider vertices on the fringe. Which one do you add next? So if we're going to be greedy about it and we want to minimize the total weight, if I'm looking at the fringe and I see edge 1, 2, 3, and 4 with weights 50, 50, 50, and 5, which one are you going to add next? The minimum one, right? So now let's go ahead and visualize this with this actual example right here. Right? Oops. There we go. Oh, good notes. There we go. All right. So it doesn't matter where you start out. I'll just go ahead and start out at A. A is now part of my tree. Okay? Now look at the fringe here. And for that, I will go ahead and use a highlighter here. I'm looking at everything that is connected to it. Now, what about everything else? All these vertices over here. These are the unseen vertices. They're not part of my tree, and they are not connected to my tree. My tree so far is, let's change this to green. Oops, nope. Green. There we go. All right, here is my tree so far. Right? And this is my fringe. And so these are my only 2 fringe vertices. The rest of these are in the dark. We haven't even seen them yet. So I'm going to consider these 2 edges on the fringe, 5 and 7. If I want to minimize connections, which one should I take first? This one, right? And let me erase this. There we go. Now, by taking that edge, I have now increased the size of my tree. Now, this is part of my tree. I wish there was a fill button, but whatever. All right. Now my fringe has changed. This one is still part of the fringe because it connects a tree vertex to a fringe vertex. But now also this one, and this one are all part of my fringe. Okay? Which one do I add next? 7, 9, 6, and 15. The choice is 6. Right? And that expands my frontier, basically. You're exploring. It's kind of like BFS, where you explore everything around you first, and then you expand your horizons until you've included in the entire graph. So I'll go ahead and include this now. Now what's my fringe? All along here. So 7, 9, 15, 8, and 11. Now I go back to one that's been in on the frontier, basically. Again, this is the frontier here. And I choose it as my next vertex. Or as my next edge, excuse me. Right. And I've now expanded the tree out here. Note what happened to 9 and 15. they're no longer on the frontier, right? Because they connect to tree edges or tree vertices. So those disappear from my frontier entirely. Okay? Now my frontier is all along here. 8, 7, 8, and 11. Well, if 7 wasn't there, then we can break ties arbitrarily, but 7 wins out. And my frontier has now expanded again to include E. And note that that 1, 8 has now disappeared from my frontier. My frontier now is these 4 edges. Which one do I select next? 5. And now that includes everything over here. And in the last iteration, what do I do? I choose the 9. Right? And that completes my graph, and now everything is part of the tree. Right? I didn't consciously do it, but green is now a proper tree. And I don't have, do I have brown? All right, well, no, I don't have brown, but there, now there's the tree now. Aha. All right, so let's go over that again. But let's think about how we can actually, I mean, visually, we could see it because we're humans, and we could say, well, that one's clearly next. And also, you colored all that stuff green, so clearly that's part of the tree, right? Now we have to translate this into something that a dumb computer can understand. So let's do that again, but let's think about potential data structures that we would want to keep track of here. Data structures and information. So when I add A, right, what is the distance from A to A? 0. Right? And I'm going to keep track of a third item here. Where did I come from? Right? Remember that, that at one point this was my frontier. And then I selected this edge right here. I want to keep track that you selected from B to E here. I want to keep track of that. So when I added E, I want to keep track that you came from B over here. Okay? But with A, there is no previous value here. So what I'm going to do is I'm going to keep track of triples. I'm going to keep track of a vertex, the weight of the frontier vertex, or frontier edge, excuse me. Right? And then finally, the third thing here is the predecessor. That is the vertex connected to this fringe or this frontier edge right here. Right? And for A, well, of course, the weight of the, if I just took A here, then what's the weight of that tree? 0, because there are no edges in it. And what's the predecessor? Well, you started there. There is no predecessor. Okay? Now what I'm going to do is I'm going to initialize all of the other vertices to the same thing. D, well, to something similar, excuse me. No predecessor because I haven't seen it yet, right? At this point, what does my tree look like? It just looks like that. Right? So I'm going to go ahead and initialize all of the other vertices here. Yeah, I'll get to that in a second. I want to go in order though. B, C, D, E, F, and G. All right. Why does it have an infinity? Let's back this up, and suppose that I start before I start out at A. Before I even start out at A, is there a frontier yet? No, because I haven't added anything to the tree. So, what distance away is B at this point? It's an infinite distance away because I haven't seen it. Right? That's just a flag value that'll help us to understand how this is going to work. And then, of course, there's no predecessor. So infinity, no predecessor, infinity, no predecessor, infinity, no predecessor, infinity, no predecessor, infinity, and no predecessor. Okay. Did I get everything? A through G? I think so. 1, 2, 3, 4, 5, 6, 7. I see 7 here. Okay? All right, now what I'm going to do is I'm going to look at everything in here and look at the weights. And I'm going to take the thing with the least weight, and I'm going to move it out of this category here. All right? I'm going to mark these as done. Okay? Now, when I did that, what I was essentially doing is I was essentially adding A to the tree. Not only that, but now I need to update those frontier vertices here. Because now I can see, right? I can see both B and D because they're connected to a tree vertex now. So I'm going to come over here to this collection, and I'm going to look at B, and it's no longer an infinite distance away. What distance is it now? 7. Well, how did you get there? I came there from A. Right? Likewise, when I consider B and reaching there from A, then 5 is much better than infinity. So I will update this to 5 and say that you came from A. Right? Now look at my collection of elements over here. There are some things that are still an infinite distance away. Those are the things that are in the unseen vertices. But these two vertices over here are in my fringe vertex set. They're on my frontier. Which one did we take next? D. Why? Because looking at 5 versus 7, we want to minimize. So what do? I take this one and I mark it as done. Now again, that is going to expand our tree here. And it's going to update our frontier. Look at everything that is connected to this. B, E now, and F. Well, I can get to B how? I can get there by 9. Is that better than just coming from A? No, so don't update that. This is still the best way of getting to B from your current tree. Okay? But now I can see, that takes care of these two edges. But now I can see E. Is that better than infinity, 15? Yes. So let's update that. E, you can get there with a weight of 15, and the predecessor here is D. Right? Why D? Because that's where you came from. That's how it's connected to the tree. D to F. F is infinity. Well, 6 is definitely better than infinity, right? 6 and D. All right? So now take a look at the next iteration. 7, infinity, 15, 6, infinity. Which one is the best one? 6. So I end up, undo. Don't want to do that. 6. There we go. And then I caught the parenthesis there, but you'll forgive me. All right? There, go back. All right, now before I update everything with respect to F, tell me, I'm organizing things here, and I'm always pulling out the thing with the next least weight. I'm always pulling out the minimum. What kind of data structure do you think will help me to keep this organized? Where I put a bunch of stuff in, and I'm always pulling the minimum thing out. What kind of it's a tree-based data structure, but it's not a binary search tree. A heap. A min heap, exactly. Now there are some details here that we have to talk about in a second, but let's go ahead and continue with this algorithm, okay? I just came from F, and so I look at the fringe set here. Right? I look at everything connected from F to unseen vertices. I don't have to worry about these over here because they've already been considered. 8 and 11. I can get to E at a weight of 8. Is that better or worse than 15? Better. So let's update it. Your predecessor is no longer D. You got there by going to F first, and the weight is only 8. What about this guy right here? G. Is 11 better than infinity? You better believe it. 11, and you came from F. Okay. Next iteration on this heap, which one am I going to pull out? This one. There we go. And now, B has been incorporated in my tree. I only need to consider edges going from B to unseen vertices here, C and E. So looking at C here, I can get there at 8. Is that better or worse than infinity? Better. So I update to 8, and I got there by going through B. B over to E at a weight of 7. Is that better or worse than 8? Better. So once again, this gets updated now at least 2 or 3 times. I lost my count, but whatever. Right? That's been updated now several times. You could have an edge that gets updated up to n times, or n minus 1 times. Right? Okay, that's all, because those are the only edges coming out from B to unseen vertices here. So my next iteration, which one am I going to pull out? This one. Oops. There we go. And that one has been decided, and it's done. There's my tree. But I need to look at all the edges going from E to unseen vertices here. I can go up to C at a weight of 5. Is that better than 8? Yep. So 5, and you came from E. I can go to G at a weight of 9. Is that better than 11? Yep. So 9, and you came from E. Now predict what the rest of the iterations are going to look like. I take out C, right? And yeah, I look at C, but does C have any outgoing edges at all to unseen vertices? Nope. So I end up updating nothing. And on the last iteration, I'm done. Now, if this were a disconnected graph and you were building a forest, you would have to start over, right? If you still had vertices over here that were an infinite distance away, that means that they're in a different component, and you need to restart your algorithm on something in that component. But otherwise, if it's one single connected component here, then you've just built yourself a tree. And note that I didn't keep track of any of the edges, did I? I didn't draw what the edges were with my pen over here. That's okay, because I've got all the information that I need to reconstruct the tree over here. For example, B. How did B get incorporated into this tree? You took the edge from B to A, this one right here. How did E get incorporated into the tree? You took the edge from B. So B and E, you took this edge right here. And also the weight is right there. It tells you how you got there. Okay? So a heap data structure allows you to keep track of this. Did I have to look at any did I have to do any cycle detection? I'll ask that. Did I have to look at the topology of the graph at all? No, other than seeing that there are outgoing edges here, and that means that I needed to update the heap elements over here. But now there's the gotcha. Given a heap, in fact, let's go ahead and talk about this since it was part of your homework a while ago. Where is it? Heap, heap, heap. A, B, C, D, E, F, G, H. I don't have, oh, there we go, min heap. All right. So that entire process was predicated on the idea that I can take a node and I can update its priority. Suppose that I want to go from 50 to, I'll update its priority to 25. I don't see 25 here at all. 20, no, that won't do anything for me. I'll update it to 3. Right? Why would I be updating things? Because this ends up being your priority in the heap. So if I'm going to take this node and change its priority into 3, altering the heap, how do I need to do that? Well, let's just assume that I was able to find the node, first of all. Now, I'm going to go ahead and change its priority, to 3. Is that a min heap? Nope. Now, how did Gomer do this? You had to come up with a counterexample for Gomer fixing the heap. Gomer only went one direction, right? Well, Gomer only went down in a min heap. Well, first of all, what about the fullness property? Do we have to worry about the fullness property at all? Well, we do have to worry about it, but I just did I make it non-full by simply just changing the priority? Nope. Gomer said, oh, okay, well, 3 is greater than 60, so I don't need to do anything now. That was Gomer's problem. And so why was Gomer wrong? Most of you came up with it. Well, because he has to look both ways. This is not a min heap. What needs to be done here? These need to be swapped. Right? And when you do that, 3, 5 goes down. Oh, no, it's ugly. 5 and then 3. Right, I'm not going to rewrite it all. If I start erasing, I'll just get the original. I've been coloring over here. All right, fine. 5. There we go. 3. Now is it a min heap? Yep, it's been fixed. That assumed that I could find that original node here. Right, let's back it up. Right. So, can you find this node for free as heaps are generally presented? What would you have to do? A BFS throughout the entire tree until you find what you were looking for. That kills you right there, because that's going to be order n, linear. The fixing of the heap goes up or goes down, it doesn't really matter. That's going to be order log n, because the depth is log n. But if I have to go through every single node to find the one that I'm looking for in the array, the underlying array that this is being represented with, that kills my efficiency. So ideas. Yeah.
Could you store all the, like once you have the heap all sorted, could you sort all the, or could you take one BFS, list it all in like a list?
Oh, okay. So 50. Map it to something. What? To the node of 50. If I did that, anytime I asked for this element, I could immediately jump to the node, which gives me right there, or node, or index. If it's an index-based heap, which an array-based heap, which it probably is. Right? So as long as I keep track of a key to a value, right, a map, or in Python parlance, it would be a dictionary, right? Then I can get this for free if it's all hash-based. Right? The only problem is when 50 gets updated to 3, what do I need to do to my map? I also need to update the key. The key then goes to the same node for 3. Right. Where have we seen that? Where have we seen that idea before? Disjoint sets. How was I able to immediately jump to the disjoint set node for free? I kept them in a dictionary. Right? So a lot of data structures internally have these other gotchas. I mean, when we look at a min heap here, and I tell you, oh, you can go ahead and use an array. That's not the end of the story, right? In order to get some other operations that are just as basic, for example, update priority, right? Update the priority to make it lower or higher or whatever. you can't just get that from the naive implementation. You have to add in and mix in another data structure. And in this case, it's going to be a hash map. So this kind of priority data structure can be implemented with 2 underlying data structures and a little bit more bookkeeping. All right?
So instead of mapping, you array, and that would work too?
No, because then where's 50 in the array? I guess you could keep a sorted array, but then every time you update it, you need to move it around. You need to make room for it, just like adding something to the beginning of an array. You have to shift everything down. That's going to be a linear operation. Now, what if it's a linked list implementation? That also kills you, because now how do you find 50? You have to, even if it's sorted, you have to start at one end and possibly go to the middle, order n. Yeah.
I guess 2 things. So would you recommend us basically
From a practical perspective, this implementation is not part of Python. Python has a heap, and we've talked about it before, and you're free to use that. I wouldn't go so far as to implement it so that it's even slightly more efficient. I mean, we can do that as an exercise maybe next week or something like that. But as presented, I would do the quick and dirty way of implementing these things. Just use the heap. If you need to update a priority,
which is
call heapify again,
okay.
right? And it'll take care of it for you. Right? A lot of these, I mean, like the disjoint set, you're not going to find an implementation of that in a standard collections library, because it is so niche, and the speed up that it gives you is not that big of a deal. Going from log n down to, or amortized constant time with dictionaries, down to definite theoretical constant time, it's not that, it doesn't buy you much, right? And all it buys you is some street cred when it comes to, hey, look at my algorithms. Right? So if you want street cred, like I just did, here's my street cred. Check out my disjoint set Python implementation. And look how cool I am. Right?
So, what combinations of things do we use for like our next assignment? 'Cause, like,
Probably a
lot of
heap.
disjoint
I mean, you need to decide which one do you want to do first. Do you want to do prims, or do you want to do Kruskals? Right? Kruskals, there's no data structures at all. You put them in the list and you sort it. Right? With Prim's algorithm, you'd probably have to use a heap. Right? But don't make your own heap. Just use Python's heap. Right? Okay? I'll go ahead and sign off now, and have a good weekend, but go ahead and